All right, so today I'm going to talk about Virial Theorem, and I'm going to talk about galactic structure, and I'm going to answer all your questions about galactic structure. Uh, let's see. So there's a reading that I'm going to go through. You guys all asked a bunch of great questions. One of you noticed that I said I was going to post a homework, and then flaked, and one of you emailed me. That's cool. I got the email, but didn't have an actual minute to post the stupid homework because yesterday was busy. So anyway, it's up now. It's okay because I took a little longer getting over distances than I intended to. Intended to. That's how long it took this time. I'm not worried about that. So it's okay that everything's shifted by a little bit. Okay, so can you guys read that? Is that too little? I can. That's the important bit. Um, so, okay. So I'm just going to go through the questions that you guys asked and either answer them or tell you that I'm going to answer them later today, which some of these I'm just going to do better. I just do a better job later. So the first one, what does scale height tell us about a population? I'll go through this in detail. The basic idea is it tells you how much energy is in that population. So I've got gravity pulling down, and that's going to flatten everything. And all of the stars feel the same gravity. But I've got other things that are pushing back up. Pressure and velocity dispersion, sigma. I'll talk about what velocity dispersion means. It's kind of like pressure. It's kind of absolutely nothing like pressure. But it's the random motions of the stars. So I'll go through that in detail. What the scale height tells you is so this is the midplane of the galaxy. This is 0. This is the ground. The scale height tells you how much energy is in that component. So a thin scale height is stuff that doesn't have a lot of temperature or kinetic energy. So like the young stellar population doesn't have a lot of kinetic energy. The dust, doesn't have a lot of kinetic energy. The dust has a very thin scale height. It has very little kinetic energy. It's also pressureless, but the hot gas is a much higher scale height because it has a lot more pressure. More on that later. Is there a superposition of different magnetic fields from different sources in the galaxy? No. Yes, but also no. There's one field, and they all just add to it. It's not like quantum mechanics where you can have a superposition of things where you have the two different states stacked on top of each other and it exists in both states at once. The magnetic field just adds. So it's just the field that's there. So yes, there's a bunch of different sources that all contribute to the magnetic field in the galaxy, which I'll talk more about in a little bit. But it's impossible to sort out which one is which unless you're like looking at a magnetar and saying, here is a magnetar, this is its magnetic field. If I'm looking at the interstellar medium, which is the crap in between galaxies and the stars, there's just a magnetic field there, and it gets fed into by all sorts of different sources. So that's something that I'm trying to get paid by NASA to study, is how to disentangle the magnetic field in the galaxy. So I like this question because I like the magnetic field in the galaxy. Are the magnetic fields uniform or changing as the universe evolves, and what does that mean? So everything is changing and constantly evolving, and there are basically no uniform static magnetic fields in the universe. They're all changing by whatever physics is going on. I'll talk more about magnetic fields later. A bunch of you had questions about magnetic fields that must have struck everyone's fancy, which I enjoy because I like the magnetic fields in the galaxy. It's one of the things that I do for a living. Let's see. What determines the result of a supernova, whether it's a neutron star or a black hole? The actual answer is we don't actually know. Ultimately, it's the mass, but probably also the chemistry and the rotation and maybe whatever's near it. And I don't really understand. Not the right person to ask, but I can tell you that the right person to ask doesn't know either. So it's not clear. It's probably the mass. So a really big object is just going to collapse directly to a black hole because if the gravity is large enough, then there's no point where the pressure is large enough to support it. So if you've got a really big black hole or a really big star, it's going to go straight to a black hole. The details there are really complicated. there's a really cool plot that somebody made. What is his name? I can picture his face, and I can't remember his name. Anyway, there's a really cool plot of stellar endpoint after the supernova versus mass, and it looks like a barcode. It's just like a random shot of whether it's a black hole or a supernova. It's just like sometimes it's supernova, sometimes it's a black hole. So we don't really understand very well. What causes our galaxy to become a spiral? That's a good question, and I'll talk about this again later. So basically, it's really easy to get rid of energy, but it's really hard to get rid of angular momentum. So if I have a ball and I get rid of all the energy, it's going to get smaller. If it's not spinning, it'll get smaller to a point, but if it's spinning, then it'll get smaller until you hit the rotation floor. So it's spinning, so it's going to keep itself in disc shaped. And that angular momentum is very difficult to get rid of. Energy, you just radiate photons and get colder. Everything radiates, everything is always getting colder, but things don't tend to stop spinning. Okay, is Zeeman effect the main way to identify magnetars? Let's talk about Zeeman for 1 second. Zeeman, and I'll do this again in a second. I have my proton, and I have my electron, and they've got an energy based on where the electron is, but it's degenerate because the energy doesn't really care about the spins, it only cares about where the electron is. Now if I add a big magnetic field, you guys brought me this nice blue chalk. Oh, that is a very nice chalk. That's very satisfying. If I have a magnetic field, then both of these spins interact with the magnetic field, and there's a difference between this state and this state. Now I have an energy difference between the electron spin going up and the electron spin going down. So if I have an excited electron and it goes to a different state, I can tell where it comes from. But the thing about the Zeeman splitting is it's incredibly weak. It's really hard to do. And it only gives you one component of the magnetic field, unless you have incredibly low noise signals. So probably. So the question up here, there was another question about Zeeman that I'll get to in a second. Maybe it was just explain Zeeman, and I'll do that better than I just did. Is Zeeman effect the way to identify magnetars? I think so. So you identify a pulsar, and then you see that it's got a very large magnetic field. But a pulsar has a very large magnetic field. So, and I think that Zeeman is the main way that they measure those magnetic fields. I can't think of any other ones that would work for a star like that. I'll show you some Zeeman measurements later. Is there a specific reason why the mass to light ratio is similar in the bulge and the thin disk? No, it's random ass chance, because the bulge is old and has this kind of complex dance of having both old stellar populations and young stellar populations, whereas the thin disk is mostly just young stellar population. So it's kind of a coincidence that the two bits happen to line right up. Is the extinction higher in the center? Yeah. And is there more dust in the bulge? Yeah. There's a lot more crap in the bulge. It's big and red and dirty. And there's a whole 8 kiloparsecs of stuff that we're looking through, because we've got to look through the whole disk. So we see all that whole column of disk. So we're looking through a bunch of it, but also there's more in the middle, if that helps. So yes and yes. Are there any other standard candles besides type 1a? Yes. All of the supernova, I think. Well, I'm not the right person to answer this question. Eric Shao or Dr. Murphy or Dr. Hoflich, they all know supernova better than I do. So yeah, some of these supernova are really consistent, and you can use them as standard candles as well. But type 1a are nice because, for a couple of reasons, they are more standard. So there are other things that you can make standard, but they're not by themselves. Type 1a are really pretty consistent. And they form in different environments, so they last a lot longer before they blow up. So they form in different environments, so they probe different things. Let's see. What are the specific distinctions between different types of star clusters? I unfortunately don't know. So this is a weeds level detail that I'm not sure about. So basically, there's open clusters, which are things that are clearly a gravitationally bound ball of stars, but not super dense. They tend to be smaller and not quite as gravitationally bound. Whereas a globular cluster is larger mass, smaller physically, smaller radius, more objects, tighter bound. That's about what I can tell you. I used to think I knew where globular clusters came from, but now I have no idea. Yeah.
Are the globular clusters also typically older?
Yeah, typically. Where did the magnetic field come from? I will explain this in super unsatisfying detail. I can explain this in very satisfying detail when you take Hydra with me in a year, because I go through dynamos and where magnetic fields come from. But I'll tell you real briefly in a little bit when I get there. What is the scale height? I don't sort these questions. I just kind of read them as they get in. So scale height, I have e to the minus z over h. This describes my galaxy. So this is the density. So it falls off like e, so it's an exponential. It goes like minus z over this h, scale height. H is the scale height, and it sets basically the thickness of the disk. If I make h bigger, then this is a thicker thing. If I make h smaller, then it's a smaller object. I'll go through that again later. Well, because I'm going to derive the scale height, and it'll make more sense. Still confused about dispersion. So I'll do this again in a minute. But the basic idea is if I take a bunch of quantities, say the velocity of my stars, and I add them all up and divide by the number of stars, I get the average velocity of the star. So for a galaxy, the average z velocity is 0 because it's not moving in that way. The average radial velocity is 0 because they're not spinning, but the average tangential velocity is non-zero because it's going on in a circle. So what you want to know is, so you know the average velocities, then you want to know how different from the average is the population. So I know what but is every star doing the same thing? Or are they doing lots of different things and they just happen to average out to whatever the average happens to be? So what we do, so you can add up the quantity and divide by the number, and this gets you the average quantity. If I add up the quantity minus the average quantity, that gets me 0. I mean, I just move this to the side, right? But if I square it, this is always a positive quantity because I'm adding up a bunch of positive things. So if I take the quantity, here my velocity, but there's lots of different things that I'll take a dispersion of. So I take the velocity minus the average velocity, and then I square it. And I add those all up and divide by the number. And that gives me how different from the average the velocity is on average. So are all my stars kind of boring and then I've got a couple that are doing something interesting? Or are they all doing interesting things and they just happen to average out to 0? That is determined by how big the dispersion is. Again, I'll do that again in a second. Please explain Zeeman, Lorentz, and Faraday rotation. I will. They're all kind of long. Zeeman, I'll do it really quick. Zeeman I just explained. So Zeeman is the magnetic field lifting the degeneracy in the atom. So when I have an atom, it's got two ways to go from this state to this state. But when you have a magnetic field, then you can tell the difference between these two ways. And then you can use that to measure the magnetic field, because you can measure the two different states. More later. The Lorentz force is just the force acting on a charged particle from a magnetic field. So F equals Q times V cross B. Maybe Q over C. Let's stick in CGS. So we'll say Q. We'll say sorry. Let's go here. B Q over C. Where Q, this is just a random mass quantity. Q here is now the charge of the electron, and V cross B is the motion of the electron. So if I have this magnetic field here, if I have a velocity in this direction, then it'll make a curl force in this direction. So if I have a magnetic field that's going this way, and I have a particle that's going this way, it will feel the force from the transverse direction. And then Faraday rotation. So this, once again, if I have a charged plasma and a polarized radio wave passing through that charged plasma, the plasma will rotate the radio wave. And I can use that rotation to measure the magnetic field strength. It requires a really large plasma to work. And I'll go through that again later. I'll show you some math with that. That's the very short answer to that. So that's coming more. Probably later today. I might not get there today. Why is the lawnmower radius larger than the Milky Way? The particles are confined by the field. Well, they're confined to something that's bigger than the Milky Way. So some of these particles, I should have looked up what the lawnmower radius is off the top of my head. Does anybody know what the radius is? It's like EB over V, something like that. That's not right. I don't remember. Damn it, I didn't look it up. So basically, the lawnmower radius is how big of a circle when I have, let's start back at the top. If I have a magnetic field, say I've got a uniform magnetic field in this room and it's all pointing up. If an electron, it gets shot into the room, it's going to feel the Lorentz force, and it will move perpendicularly to its motion. So it's got a velocity in this direction, so it'll feel force in this direction. So it'll go in a circle, because it's always going to feel a force perpendicular to the velocity, so it will go in a circle. The radius of that circle is the lawnmower radius. If I have a higher energy particle, it's going to make a bigger circle before it turns around. So if I have an incredibly high energy particle, then it doesn't matter what the magnetic field of the universe is. Its lawnmower radius is going to be huge. Some of these cosmic rays have the momentum of a baseball that's been hit by a batter. So like 100-mile-an-hour baseball. It's the proton with that same momentum. So some of these particles have really crazy energies. Okay. More on that later. How far above the surface of the Earth are cosmic rays an actual concern? Right here. I have a friend who was hired by Sun Microsystems to take the code that we run. So I've got this computer code that makes simulations of stuff astrophysics, so like formations of galaxies and stuff. They had him just run this computer. It's really rough on computers because it's very memory intensive and it's very processor intensive. So he took this code, which is the same kind of stuff I do science with, and just filled up the computer and just let it run for a couple of weeks. And what he was looking for were cosmic rays changing bits in the memory of the machine. So cosmic rays can impact computers on Earth by changing bits. There's a super famous speed run of Mario 64 where I'll go through this, and you can go through this after class. But the speedrunners really understand the details of the code that they're working with, so that they can screw around with it. There's one particular speed run where a guy is jumping up to glitch through a panel, and instead something changes in the memory state, and he's suddenly an entire floor in this castle. He's an entire floor above where he was supposed to be. And they went back and said, well, how the hell did I do that? And they sorted out something must have changed the memory state so that he was in the right spot. So cosmic rays are a problem on Earth. Not a huge problem. Like this, now we have an unbeatable speed run for Mario 64. Like no one is ever beating that again because of this. That's a super low grade concern. If you're in the atmosphere, cosmic rays, basically as soon as you get very high up, cosmic rays are a big problem. All satellites have to be really radiation hardened, so they've got to have real thick shielding around everything. Transistors have to be real big. So charged particles from the sun and from the extragalactic cosmic rays, there's all kinds of charged particles that totally screw everything up if you're above the atmosphere and not properly shielded. Fortunately, it's relatively easy to shield against cosmic rays. Well, that's not true. Some of these things really will go through everything. But there's not a lot of them. So, yeah.
Well, silly question.
Uh-huh.
I heard that cosmic rays can't pass through concrete.
That is not true. There are cosmic. When we say cosmic rays, there's a huge spread of energies. So low energy cosmic rays can't go through concrete. Higher energy cosmic rays will. So when you have something like, if you're looking for neutrinos or dark matter particles, you got to put it through miles of stone and bedrock, and then a bunch of concrete, and there are still particles that'll get through, but only the really rare ones. So more concrete means you get fewer of them, but it's almost impossible to screen for all of them. Why is the bulge a bar? I'm not going to go through bar dynamics very much, but it's a dynamical process where things get on these really high eccentricity orbits and the stars just start racing around in a really skinny thing like a racetrack. I have never sat down to really understand why they do that because I haven't had time to. What is velocity dispersion? I'll talk more about that in a minute. And what is the random motion of the stars? It's the random motion of the stars. So the stars in the galaxy have a couple different kinds of motion, superimposed, but really they just have one velocity. But the velocity comes from different things. There's a uniform velocity of the stars going around the galaxy, and then you have random velocities of them interacting with each other, not going on a smooth path through around the galaxy, all kinds of random interactions. So there's random motion in the stars too, which actually dominates the ordered motion in a lot of stars. What is the interstellar medium? The interstellar medium, or ISM, and I will refer to it almost always as ISM, is the gas and dirt and sometimes cosmic rays and probably magnetic fields that are between all the stars in the galaxy. So it's mostly gas. Why are type 2 core collapse supernovas only found in spiral and irregular galaxies? I'm not answering this question right now because it's such a good question. I'm going to let you guys sort this out. Let's see. Does anybody have any ideas why, real quick? Why? Yeah.
Isn't it because the elliptical galaxies are too old?
And what does that mean?
They've already had it happen.
Yeah, no, they're lower mass stars, right? So they can't, like, if they live that long, they're not going to explode into type 2.
So yeah, did everybody follow that? Younger galaxies, younger stars. Type 1A take forever, like astronomically forever. Type 2, a core collapse supernova, explode really close to the end of the stellar lifespan. So why does that mean spiral and irregular galaxies? Because those are the galaxies that are forming stars. Core collapse supernova come from massive stars. Massive stars come from star-forming regions. If you don't have star-forming regions, you don't have any massive stars. You can't have any core collapse supernova. So anyway, this is a great question that I'm going to come back to because it really ties a bunch of interesting physics together. If stars form the elements through iron, where do the rest come from? Also stars, just not main sequence. They form up through iron when they're on the main sequence. And then other things get formed after they leave the main sequence. So there's a couple of different places. So there are AGB stars, which are big fluffy red dudes. They make some stars. Supernova makes some elements. Some rare elements like gold and platinum, you can't form in stars. You form in neutron star mergers. This is one of the most exciting things that we've seen since I started teaching this class. In 2018. Really shortly after they turned on the gravitational wave observatories, saw a neutron star merger, and every telescope on Earth pointed at this neutron star merger, and we watched gold being produced for the first time. We've never seen gold production in the universe, and we got to see it. 10% of all astronomers are on these papers that came out. They're incredibly important papers. Like literally every astronomer was talking about nothing other than this neutron star merger. So that's where some of the stuff comes from.
I mean, it was really cool. It makes sense.
Yeah, it was really amazing. And it was really cool because the gravitational waves told us where to look first, and everybody was pretty stoked about that. What's the difference between an open and a globular cluster? Just the size, really, or the number of stars. And what causes the bulge? Smashing crap together, really. I don't know if I have a good answer for you right now, but a good answer will come over the course of the semester. And what's the age of the bulge? The bulge, I mean, it's a thing that's old but has young stuff in it. So hard to say if you're talking about which part of the bulge, because there's clearly young star forming regions in it, but it's clearly at least as old as the galaxy, probably older. Okay. Anybody have any questions about questions? Let us talk about the Virial theorem. I should state the Virial theorem. Let me redo this slide. Let's. Do I have it somewhere I can? Oops. Nope. There you go. 2ke plus u equals 0. So twice the kinetic energy plus the potential energy is 0. Another way to say this, and the way we think about it more often, is the absolute value of twice the kinetic energy is the absolute value of the potential energy. Why is that? Well, potential energy is negative most of the time. For stellar systems it is. This is true regardless of whether we're talking about gravity in a sense, but we really only apply it to gravity. So you guys talked a little bit about Virial theorem and Intro to Astro, yeah? So I'm just going to go through where it comes from because it's useful and important. So the first thing we do is define this thing called the moment of inertia, which if you haven't taken mechanics yet, you probably won't have seen much. Probably saw it a little bit in 2049 or 48. So the moment of inertia is what? It is it's kind of like the mass, but for spinning around. So, oh, I'm over there.
Oh,
yeah.
Oh man, I forgot it. I can't believe I forgot it.
What the formula is?
Yeah.
Does anybody else know? mr squared. That's it. That's okay. You just started. That's cool. Mr squared. So this is, I have a thing, and I have an origin. Now the origin matters. Where you put 0 matters, but not a ton. And I've got a bunch of particles, and I'm going to measure where the particles are, weighted by the moment arm. So this is like how hard it is to rotate an object. So we're left with things like torque equals I times alpha. So torque is the twisting force, alpha is the acceleration of the rotation, and I is the moment of inertia. So I is the resistance to getting spun up and rotating. We're going to actually throw it away. I'm going to talk about this thing, and then I'm going to throw it away. But it describes two things. So first, it describes the resistance to motion, resistance to rotation, and the second is it describes the configuration. That only makes sense from these things. So it's the resistance to rotation. It also describes the configuration of the stuff. So if I have all of my stuff is in a shell far away from the origin, I'll have a way different momentum, moment of inertia, than if all my stuff is at a point at the center, even if this mass is the same. So I can push them around the same, but I can't rotate them the same. So we'll start with this moment of inertia. We'll ask, what's its derivative? So I dot, we'll take a derivative of that, is the sum on I. This is the mass of the particle I, and this is the radius of particle I. Sum on I of the mass of a star doesn't change enough, times 2 r dot. Here, I'm gonna drop the subscripts because they get confusing. I'll pick them back up in a second. Sorry, I'm a little wrong. This is particle I, not component I. Doesn't make a huge difference now. Move this 2. Well, I want that over there. Let's take the second derivative of this, and this is what? Second derivative of this is going to be mRi double dot plus mRi dot squared. What's this? What is Ri dot? R dot equals. Everybody's good with me using dot, yeah. Dot means time derivative. R dot is our dRdt. What do we call that? Velocity. So this is velocity. Mr squared is mv squared is what? Kinetic energy. So this is twice the kinetic energy. And this is what? R double dot is what? Acceleration. How does acceleration relate to gravity? Not quite all the way to the work. So acceleration, R double dot, let's say mR double dot, is force. Okay, the cheesiest derivation, this is how you remember that you're on the right track. Oh, I gotta click on the right thing. Okay, don't actually do this, but the force is gm over r squared, and the potential is gm over r. So if I multiply by r, it just kills one of the r's, right? It's like basically what we're doing. Yeah.
When it's the force, is it supposed to be negative? Because I thought it was only negative for the potential energy.
No, the force is negative. So the force, I should be specific. So the force between I and J is G times Mi times Mj over Rij, Ri minus Rj. Absolute value of that squared times Rij. And the minus sign is important for the r hat. That tells us that the force is attractive. It's pointing together. So then when I take a F equals minus grad U. So this is a relationship that's true in all kinds of places. If I have a potential, the force is equal to minus the derivative of potential. And since this goes like 1 over r, the derivative goes like 1 over r squared, and we pick up a minus sign and then another minus sign. So the first minus sign kills this one, and the other one takes it out. So we got 2 minus signs. So this is the cheesiest derivation. A slightly better derivation that doesn't involve integrations that you're kind of waving your hands past. So I start off with the sum on all the particles Ri times Fi. Now I shouldn't erase that, is the sum on J of G times MIMJ over Ri minus Rj, this quantity squared. So this equals sum on I, Ri, sum on J, Fij. So this is funny because it's symmetric. So because this is symmetric, I can say that I'm just going to do the integral over half of them, and I'll do it twice. So this is now sum on I, Ri of sum on J, 2 Fij minus sum on j equals n over 2 to the n of Fji. So I'm only doing half the sum, and I'm going to flip it around halfway through. Done the same thing, just using the symmetry of the force. Fij is minus Fji. Then I'm going to expand this guy out to both things and change my indices. So I'm left with sum on I, Ri, Fij minus sum on j, Rj, Fij. So I switched the indices, and then I changed I to j because I can just relabel things. And I'm left with this. And then this is equal to the sum on I of Ri minus Rj, sum on I, sum on j, this is sum, times Fij, and then this is what properly cancels the denominator, because the denominator is actually the difference between the two forces. Does everybody follow that? At least for the most part. Basically, we start off with R times Fij. We do a little stunt to make this thing look like that so that we can actually cancel this, but really the idea is we're just undoing F equals minus grad U. R times F is kind of like the integral of that, because it happens to be a power law. Okay, so what does this tell us? So what we're left with is this here. 1/2 I double dot equals 2ke plus u, maybe pe, however you want to call it. Now, this quantity, I should be on the screen. This quantity, so this statement that I've written down, 1/2 I double dot is twice the kinetic energy plus the potential energy. This is a true statement and is equivalent to F equals ma. It's not any different. I got it from F equals ma. It is a accurate statement. So I didn't have to do any approximations, and I didn't really wave my hands past anything. So this is true. But it's basically impossible to use. And it's hard to get insight out of this. Because what is I double dot? I don't know. But what I do know is that if I have something that goes around in an orbit, in a closed orbit, if I integrate I double dot around a closed orbit, what do I get? Well, I get it right back to where I started. So I better get back to 0, because this is the integral over the full derivative of something. And that full derivative of something has to be the same when it gets back to the end. So remember, the integral of df equals f at the endpoints. So when I integrate I double dot around one orbit, say I've got a star going around a black hole, or a bunch of stars going around the central potential of the galaxy, if I integrate the orbit, this integrates up to 0, because I've got a closed orbit. So if I do an integral over ensemble or orbits of this quantity, I can get this term to go away. And then I'm left with something that's useful. Now I have a nice tight relationship between the kinetic energy and the potential energy. Now you can't always use it if the thing is changing. If I double dot is really substantial, that means the configuration is changing significantly, then you can't use this. But if the configuration of the stars isn't changing appreciably, then you can use Virial theorem, and it works out pretty well. It describes things in equilibrium, but really it's a statement about force balance. What it's saying is that statistically and averaged over the whole system, the forces all balance out. Even though the stars might be moving, the average of the forces all balance out, so that the net object isn't moving. So say we've got a globular cluster, a bunch of stars. The way to think about it is globular cluster. So this has like 10 to the 6 stars, and it's like a parsec across. So it's not a huge object. I mean, it's a huge object if you don't have space in your living room for it, but it's much smaller than a galaxy. What are these stars doing? The stars in here are on orbits around the central potential. So all of these stars come together to make a potential phi, and that potential is deep. And the stars just rattle around in the potential, just like skateboarders in a half pipe. Right? So they go over here and they get a bunch of kinetic energy, come back, there's a bunch of potential energy, then they go over here and they have a bunch of kinetic energy. Yeah, so on average, even though each individual star is doing something crazy, on average, the thing isn't changing very much. So we can say that the kinetic energy balances the potential energy. Yeah.
Can you still say that I double dot is 0 over the whole loop with non-conservative forces? Like if we have different strengths of gravity?
Well, gravity's always
Yeah.
conservative.
But
But if you have something else like magnetic field,
Yeah.
you can bake a magnetic field and non-conservative forces into Virial theorem, but then you get integrals that don't go away. So if I want to, so I just had point particles. I can do this again with magnetic fields and gravity, and not throw as many things out, and I'm left with a much worse expression, but it still tells us something. So, how do we get rid of it? What else did I say in this slides? Yeah, so integral of d foo is foo. So the integral of the derivative of a thing is just the thing at its endpoints. So if you're at a closed loop, the endpoints are the same. So whatever it was is 0 as long as things aren't exploding. So we're left with that order. Let's see, do I care about anything? Oh, this point is important. So the moment of inertia is an average. You integrate out over the particles' identities. So I don't really care which particles are doing what. They're moving around. So the individual particles are moving, but the average density of particles stays the same. I've got a particle that moves out of a region of space, another one moves in. So in a big enough region of space, you can always say that the motion's the same. Okay. Anybody have any questions about Virial theorem? Milky Way. I don't need you. Let's make this bigger. So, what does the Milky Way look like? We need to know what the Milky Way looks like if we're going to understand what other galaxies are like. And because we're in it, we can see it easiest. It's got a bunch of components. So, it's the thin disk like a pancake. And it's a thin disk because it's got a lot of orbital angular momentum and not a lot of energy keeping it around. Now the gas pressure is actually really low, so the gas pressure is not really what's causing a lot of the processes. It's really the velocity of the random motions of stuff. So this is another nice spiral galaxy. This is the Sombrero galaxy. I put this one up because you can actually see it. You can see this looks like a disk. It's pretty thin. This one has a monster bulge in the center, and I don't really understand why it's quite like this, because there's really no dust out to this like crazy high radius, so it's kind of weird, but regardless, this is a disk galaxy. So we're going to talk about what's in the galaxy. We'll talk about why a disk, then we'll talk about the bulge really quickly. We'll talk about the halo really quickly, and we'll talk about the ISM for as long as we feel like talking. I like the ISM more than most people that you've met. Okay, so why a disk? Why don't I do that for a couple slides? So first off, Poisson's equation, del phi squared equals 4 pi g rho, is how gravity works. You probably haven't seen gravity quite like that, but it's the way I like to use gravity. So phi is the integral of rho of r over r phi of r dr. So I just add up all the density. And then del squared phi of r, the second spatial derivative, this is the vector derivative, right? Del squared of phi is 4 pi g times rho times the density of stuff. This is equivalent to saying that the force is g m over r squared. But you got to do a little bit of calculus to see that. I'm not doing that right now. We'll just take Poisson's equation as word of God. This tells us how gravity works. This tells us how gravity works as well. So, my density, okay, I will interchangeably call density n and rho. Usually I mean number density when I write n, and mass density when I mean rho, but the difference is just the mass of a star, which is usually cancels out. So I will be a little sloppy about n versus rho. I apologize. N and rho are both densities. So the density is observed as a function of z, goes like e to the minus z over h. What does that look like? That means that this is z, this is n, means that it goes down like that. And there's some scale height h where the density falls off to e. Okay, e is like 2.7. Where it falls off to e over the central density. So the scale height is where the density has gone down by like half. Why is it an exponential? Which density is this? So if my disk is like this, here's my rotation axis. Here's my midplane, looking at the edge of the galaxy. The z component is away from the midplane of the galaxy. Now, if I look at this as a function of radius, n of r is also an exponential. E to the minus r over hr with another scale height. So I get an exponential vertically and an exponential radially, but they're different exponentials. So why do I get an exponential? So here, so if I have this differential equation, dn dz equals minus a times n, we can solve this for n of z, and it equals what? Everybody do this in your head, and then somebody yell it out. E to the minus a times z. If I take one derivative of this, just the minus a comes down. I say without any irony or exaggeration that this is the most important differential equation that you come across. This I don't know. Lots of life comes from this. So why do we get an exponential? Because I'll leave this up here. We're basically one-dimensional system. That solves that equation. So if I want to know what things are doing, I start with f equals ma, because that's kind of where I start everything. F equals what? So if I've got, let's set up the system. I have the ground. The force of gravity is just G, which is we're going to call it uniform. I'm going to put this one over. I'm going to put this M over here. And I got some pressure in this gas. So this gas here has some pressure. So what's pressure to you? What does pressure mean to you?
Like how many times, like let's say an atom could bounce on the walls of the container?
Yeah, that's a good way to think about it. So atoms bouncing off the walls of the container. Now we're in outer space, there are no walls. So it's bouncing off of whatever, yeah.
It's like a density, right?
It's like a density, but density and pressure are related to each other, but they're independent of each other. So it's a property that the gas contains. What are the units on pressure? Right, so it's a force per area. What's the relationship between newtons and ergs and energy? Joule. Unit-wise. Think about just units. What's the difference between a joule and a newton? A joule is a newton times a meter. So pressure is force per area, or newton per meter, or energy per volume. I put a meter here and a meter here, and I get my meter times my force gives me an energy. Force times distance gives you energy. Area times distance gives you volume. So you can think about pressure as a force per area, which is a fine way to think about things, but it kind of breaks down when we get into outer space and there's no surfaces that things are pushing on. So it's really good to think about the pressure as an energy per volume. Now, not exactly, there's a factor of like 3/2 kicking around to turn it into an actual energy, but it behaves like an energy per volume. And that 3/2 is really just accounting. Just making sure that you've got all the things that are giving you energy. I guess still got 20 minutes. So pressure is an energy per volume. Pressure by itself doesn't do anything. The pressure in the room right now is not changing your life one bit. But if it changes, then you get pushed around. So P by itself doesn't matter, but grad P minus grad P is a force. If I have a bottle and I have my pressure on one side is larger than the pressure on the other side, it's going to move. So force is minus grad P. And actually, force is actually rho grad P. We've got a per unit mass kicking around the world. I'm not going to worry about it. So we'll do this better 4 seconds. So dP dz. Oh, I'm sorry. That row, ignore that row. That was incorrect. Squirrel brain insisted on putting that row there, but then erased it. So dP dz is the force, right? Yeah, that's just, this is equal to minus g, my vector, my gravity, times rho, in the z hat direction. We only have gravity in z hat. I don't need z hat. So this is pressure pushing, and this is gravity pulling. How many unknowns do I have in this equation? Let's say that G is given. Density and pressure. So I have two unknowns and one equation. What's the equation that relates density and pressure? The ideal gas law. What's the ideal gas law? PV equals nRT. So this is an N. What is this N? When I wrote it down like this, what is this N? Ignore everything else I've said. Remember back to your chemistry. The number of moles. I want a density. How do I make a density out of this? Divide by volume. And where's the volume? On the right hand side. P equals rho RT. This is number, this is mass, so I gotta divide by the mass of the particle. Okay, that's fine. And really I don't like R. I like K. Small difference. What's the difference between R and K? So R is the gas constant. K is Boltzmann's constant. They're different by Avogadro's number. Because R is energy per mole, and K is energy per particle. R is in joules per mole Kelvin, and K is just in joules per Kelvin. I'm an astronomer, I'm not afraid of 10 to the 38 as a number, so we'll deal with particles instead of moles. Moles are much more useful if you need to have like a bottle of this stuff. So the ideal gas law says that that P equals rho KT over the mass of the photon. So we'll drop this in here and we'll get an equation for rho. So what all gets left? So I'm left with dP, which is KT over M, KT over M, all comes out, and I'm left with d rho dz equals minus G rho. Let's move this stuff over here. I'm left with d rho dz equals minus G M over KT rho. This is one of my favorite differential equations. Has a lot. It is hard, my favorite differential equation. And this we can write down. Rho equals rho naught e to the minus Gm over KTZ. So we'll rewrite this as rho naught e to the minus z over hz, and hz is the scale height, is equal to kt over gm. So you think about this equation like a family of equations, and hz is the knob that I can turn. As I turn hz up, then this gets to be a less aggressive of an exponential, and so the whole thing gets bigger. If hz goes down, then this falls off faster. So this is why we're left with basically an exponential. The only thing that really matters is the distance away from the midplane. That's the important thing. Let's see. Now, sometimes I'm going to talk about the gas, and sometimes I'm going to talk about the stars. Stars are zero-dimensional and don't bounce into each other. They don't have any pressure. There isn't a way that I can cook up a pressure that makes the stars look like a pressure, except for the fact that I'm just going to pretend that velocity dispersion works just like a pressure, because what's pressure? Pressure is the random motions of the particles, right? I've got a bottle of gas. The pressure is a measurement of the chaotic randomness of the motion of the particles. More motion of the particles, more pressure. So we're going to make a proxy for the velocity dispersion. We're going to treat that like a pressure. Let's see. Where am I at my slide deck? Is this consistent with my flow? The full, to really do it properly, so I did this with this kind of cartoon. To do it properly, you need to integrate Boltzmann's equation, which I'm not going to do. Let me come back to that. No, I'm going to do that now. Yeah, so this is why an exponential. Why a disk? What kind of disk? Well, you remember from 2048, I think, how do things go in circles? So if I've got something that's going on a circle, it's got some velocity. It's staying on a circle just straight from geometry. What is the centripetal acceleration for a thing with a velocity v to stay on a circle with radius r? Right. Centripetal acceleration is v squared over r. This might have been how Hopeflake derived Virial theorem. I'm going to get there in a second. So the acceleration is v squared over r. The force gmm over r squared. Ma is m this. F equals ma. So I get mv squared over r equals gmm over r squared. And I cancel stuff out. And I'm left with v squared equals gm over r. Circle this until it gets comical.
It's already been comical.
No, the laugh track hasn't kicked in.
Aww.
This is Virial theorem. You see why? Well, this is the kinetic energy. This is potential energy. This is the cheap way to derive Virial theorem from a thing going around another thing. But it gets us the same answer. This is still 2ke, and this is still the absolute value of the potential. This is the most important equation I'm going to write down all semester. We're going to come back to this all the time. V squared equals gm over r. Is a statement about kinetic energy and potential energy. So this is why things are in a disk, because it's virialized. So it's going to start to be a disk because I'm going to have a thing like this. So virial systems like to make disks because they like to be in force balance. So this is a statement about force balance as well. That's how I got here. Okay, so here is a picture of the different disks of the galaxy. I love this poster because it shows you a whole bunch of cool stuff. And actually, okay, cool. And I'll get to dispersion in a second, and then I'll be done, I think. So what this shows you is the different disks in the galaxy. So what I want you to really focus on this radio continuum, and then look at this atomic hydrogen. Now what are these two things doing? They're measuring different things. So the radio continuum is measuring the thermal processes. And the atomic hydrogen is only measuring cold hydrogen. How do I know it's cold? Yeah, because it's atomic. And 21 centimeter line, you're right. So those two things go together. Why do I know that it's cold? Because it's atomic. Because if it's cold, it's going to be atomic. And if it's hot, it will be ionized, because the gas will just ionize it. This sets the scale of what I mean when I say cold and hot. It's got to be like 10,000 degrees to actually ionize, so hot is actually pretty hot. But you'll see how much thinner this disk is than this one. So these are all different images of our galaxy. This is in the book, isn't it? No? All right, that's all right. This is different images of our galaxy in a bunch of different radio bands, from low energy radio waves to high energy gamma rays. And you can see that as the energy, the process changes, and it's not strictly these are low energy processes and these are high energy processes, though that's a good ballpark. Yeah, that's a fine ballpark. But you can see that different things have different thicknesses. So the molecular hydrogen it's kind of hard to tell from here, but it's even thinner than the atomic hydrogen. Why? Okay, so I derived this. Where'd it go? This here. My scale height, I derived as KT over GM. KT over GM. If this is the only thing that I have in my system, then a bigger scale height comes with a bigger temperature. So a hotter gas has a thicker scale height. And that's what we see here. So the atomic hydrogen is hotter than the molecular hydrogen. Molecular hydrogen is really cold. It's like 10 Kelvin. It's all really cold stuff. The infrared traces dust. The near infrared traces bigger dust, so it's fluffier dust. So the near infrared is a thicker disk than the far infrared, which only traces the very biggest dust grains. The very biggest dust grains settle down to the midplane, just like dirt finds its way into the corner of your house. All the dust in the galaxy finds its way to the midplane of the galaxy, because they're big particles and they're too big to be pushed around by the pressure. The optical is kind of a bummer because you've got all of the stuff that's in these two pictures actually in the way of this picture. So that's kind of a drag. But you can see that the optical light is pretty high. The X-ray light is very thick, and the gamma rays are also very thick, but you notice this is a really grainy picture because gamma rays are hard to measure. So that's what the different scale heights do. So the different scale heights have to do with different physics in the gas or a stellar population. Now I'm going to relate temperature to, so I was just talking about temperature. Stars don't have pressure, so I can't really talk about pressure of stars. That doesn't make any sense. Let's look at, I can't make it quite through a lecture anymore on this battery.
I'm having the same problem. I think we have the exact same MacBook, and I'm starting to hate it because it doesn't even make it through like a class.
Awesome.
Yeah, it sucks.
Yeah. Why are you so crunchy? Yeah, this is the weakest of their laptops, I think. The ones from 2015 were real banging. But my graphics card died on mine, or I would still be using it.
My dad had 2015 MacBook Pro graphics card died. He had to get a 2019.
Yeah, I was super bummed. I had to get this crap instead. And it's like, man, this is just not as good. However, they very smartly keep me in the ecosystem by having Keynote be a vastly superior product to anything else out there that does anything like it. Where was I going? Okay, so this I'm talking about temperature. Let's look at ideal gas law for a second. And I'm going to tell you that the ideal gas law is really cool. And I was teaching this class. I came to this realization like in the middle of lecture. But what are we talking about? PV equals N units T. Pressure is energy per volume. Now, I'm going to put a little bit of quotes around there because you can't just like directly drop in energy per volume. You got to make sure that you've got all of your degrees of freedom accounted for, so there's a factor of like 3/2 that's kicking around. But aside from that, pressure is energy per volume. Let's look at this. What is temperature then if pressure is energy per volume? Well, but what's the left-hand side say? The left-hand side is pressure times volume. So that's a total energy. If I have a pressure per volume and I multiply by a volume, I get a total energy. So this side, total energy. I have an equal sign, which means that this side also is the total energy. But this is temperature times the number of particles. So I'm going to think about temperature as energy per what? Particle. And this occurred to me as I was teaching because nobody had ever said it that way to me before. but it's obviously that way. This is pressure times volume, that gives me a total energy. This is number times temperature, that gives me another total energy. So temperature is energy per particle. So now, okay, now I'm good, because my stars aren't a continuous fluid. They don't bounce into each other. They don't really have a pressure. But I can do this and jimmy a pressure in there, because I can certainly talk about the energy per particle. The energy per particle is 1/2 mv squared, right? Where v is the typical velocity of the particle. So we'll just relate. We'll just say 1/2 mv squared is 3/2 kt. Okay, this 3/2 you got to take thermo to get that right, but it's basically for every degree of freedom I get 1/2 kt, and I've got x, y, and z, 3 degrees of freedom, so I get 3/2 kt. So this is a super useful relationship that relates the velocity of the particles to the temperature of the gas. This is going to be an effective temperature. It's not really a temperature. So then, my scale height, which I'd said originally, h equals kt over mg, right? Yeah. Is equal to what? We'll just drop this in here. So kt is just mv squared. This is just v squared over 3g. So this relates temperature and the velocity of the particles. Now this is v squared. It's not the velocity of the particles. It's the velocity dispersion of the particles. It's squared. That's why it's the dispersion. And the velocity dispersion is the random motion. So I've got this disk of stars, so I have this population of stars, and my stars are doing all kinds of crazy crap. They're going around in a circle, but they're also fluctuating in and out. Some of them are on elliptical orbits, some of them are on really elliptical orbits, some of them are on really round orbits, some of them are coming up and down, some of them are in binaries, some of them are shot out from a companion. So we've got all of this random motion in the galaxy. Let's see. So there's a whole lot of values that the velocity can take. So we want to know about what velocities can it take. So okay, z is out of the plane, x is the tangential velocity, and r and y is the radial velocity. Then what does vz look like? Well, its average is 0. Otherwise the galaxy would be moving. And they are, but that's dumb and boring, and I don't care about it, so we'll just take off that velocity, so the galaxy is not moving. So the average z velocity is 0. The average y velocity is the radial velocity, also going to be 0. Now the y motion is not 0. If I pick a particle, its radial velocity is non-zero. But I pick another particle on the other side, and it's coming in while this guy's going out. So on average, the size of the galaxy stays the same. Vz is the tangential velocity. It has an average that's not 0, because you're going around in a circle, and a dispersion that's not 0. So we could talk about the average Vx, which is going to be what? Go like mv squared over r. It's moving on a circle. The average of vy is 0, and the average of vz is 0. But the average of vx squared is going to be not that. We need the average of vx minus vx bar squared. So we take the average and we subtract everything out, and we get a number that's bigger than 0. And the same for y and z. So we get dispersions for y and z that are bigger than 0, even though the average motion is non-zero. And it's that random motion. So I want to say v squared, and this isn't the mean v squared, this is the dispersion v squared. So this is like how typically is a thing going. Okay. I will pick up here. Does anybody have any questions about any of the things that I just said? I'm gonna stop. Let's see. Nothing is due, right? There's not a reading.
There's a reading.
There's a reading. That's just fine. I will go through it, but I probably won't get to it. Yeah.
Can I look at
Oh, this one. This isn't Boltzmann equation. This is just the
what's
math.
the one underneath?
Which one? This one?
Okay, that was
This is the math where I did all the slide. This is the slide where I did the math.